Okay, folks, I'm going to do a quick little video that I'm calling 4 views on arc length. And the first 3 of these views are geared for somebody maybe in a Calc 2 class, and the third view is geared towards somebody who's taking a vector calculus class. I think all 4 of these views are important, and we'll see why I think the last one is probably the most important view for looking at arc plane. So let's go ahead and look at a curve in the xy plane, and I'm going to do all of my illustrations here in 2 dimensions. So let's say we have a curve like this in the xy plane, and let me actually exaggerate that a little bit. I want to have that it's a function in both x and y. So we can think of this curve as starting at point P and ending at point Q, and maybe point P has the x coordinate of A, and point Q has the x coordinate of A, and then for the y coordinate of point P, maybe we'll call C, and we'll call the y coordinate of point Q D. Okay? So I want to do this because I want to make sure that this function is strictly increasing or strictly decreasing in both the x and the y direction. So what I need here is a one-to-one function. Now, folks, the requirement that this be a one-to-one function is really only applicable for the first 2 viewpoints that I'm doing. And what I would say is that if you have a function that's not one-to-one, or if you have a curve that's not one-to-one, in fact, let's go ahead and label this curve. We'll give it the name C. Let's say you had some other curve here that isn't one-to-one, and in fact, if you thought of it as being a function of x, it wouldn't actually, you couldn't actually represent it as a function of x, or you couldn't represent it as a function of y. If this were the case, you actually have 2 options. Okay. The first one is probably the most straightforward idea, and that is simply to split the curve into several one-to-one curves. So you might, if you were doing this with respect to x, well, you could split it here, for instance, and maybe you split it here, and then maybe you split it again here, and then you split it here, and so you'd have a bunch of one-to-one curves. The other option is to parameterize the curve. And I'll go ahead and show this now because we'll actually use a parameterization for basically our 3rd and 4th viewpoint here. So what is a parameterization? Well, that's an interesting question that I don't want to get into, but let's say one way to look at it is we're going to, rather than thinking of this curve as existing in just 2 dimensions, in 2 space, here we have x and y, we're going to think of it as a 3-dimensional object where the 3rd dimension is time, and time will be the independent variable here, and then the trace or that the function creates will be our curve. So one way to say that is we take our time axis t, and we're going to look at, say, time values between time t equals alpha and beta, and just for fun I'll stick a little t0 in there. So then the way we look at this is that the parameterization is some function that maps from R1, this is the 1 dimension, to R2. And so maybe here, let's go ahead and let me draw that little curve that I had before. So we'd have maybe something like this, like that. And so maybe this would be the point where t is equal to alpha, and maybe, I don't know, maybe the t equals t0 shows up right there, and here we have time equal to beta. And so you imagine this curve being traced, and we like to think of t as representing time, and so you could imagine, like, if in sort of real time, this curve being sketched out for you, and that's a parameterization of this curve. So if I gave the parameterization a name such as p of t, again, what I'm saying is we think of it as mapping from R1 to R2 in this case, and that works by taking the independent variable time and mapping it to some ordered pair, where the ordered pair is described by the functions x of t, comma y of t. So it turns out, folks, that requiring this curve, like I did over here, to be strictly one-to-one in both the x and y direction isn't actually necessary if you do a parameterization, and that'll be the 3rd viewpoint we do. Or you could also think about just simply chopping it up if you want to into several different curves, C1, C2, C3, and C4, and then you would add up the lengths of each one of those curves to get the arc length. So this isn't really that big of a restriction, but it does make some of the statements I make a little bit easier to say. Okay. So what is our strategy? Well, our strategy is to think of chopping this curve up at several points, several different increments, and then looking at the straight line connecting 2 points on the curve. And so if I were to zoom in on, let's say we zoomed in on this segment right here, so we've got our, our x-axis, x and y-axis, and we zoom way in on this. There's the curve, and we would have some segment instead that we're actually interested in computing. And so we'll call this segment right here, I'm going to call this, and I'm going to use DL. A lot of times DS is used here, but I want to just use DL because when we sum it up, we'll go ahead and call L the length of the curve. So what can we do? Well, if I'm exaggerating this, notice we've got this x-coordinate of this point and this x-coordinate of this point, and so what we have here is the difference between these two x-coordinates here. I could call that distance dx, and the distance between these two y-coordinates, I could call that distance dy. And so we have here, if we were to imagine kind of extending these lines outwards, we could think of this as creating a right triangle. I'll put it in green here. Here's this right triangle. And so because it's a right triangle, because we chose to do this with dx and dy, we can go ahead and use the Pythagorean theorem here, which says that the length of the hypotenuse, which I'm representing as dl, that quantity squared is equal to the sums of the legs of this triangle squared. So you get dx quantity squared plus dy quantity squared. Or if I solve for dl, we get this expression that I'm going to use over and over again throughout the rest of this video, that dl is equal to the square root of dx quantity squared plus dy quantity squared. So at least this viewpoint, for options 1 through 3, this viewpoint requires the Pythagorean theorem, and that's really what everything hinges on. Okay, so I'm going to go ahead and do some algebra on this expression. It's sort of a formal algebra. It's not really, some purists would object to the way we're going to do this, but that's okay. It's just going to be, to build the arc length formulas, and for this to work, I need dx and dy to be positive. Let's see. So let's assume dx and dy are positive. Okay, so I'm going to do some just algebraic manipulation here, and you might say that this is kind of hocus pocus, and I wouldn't argue with that, but it's going to lead us to the traditional equations that we use for arc length. So notice that we start off by saying dl is equal to dx quantity squared plus dy quantity squared, and so what I'd like to do is I'm going to take this expression now, and I'm going to multiply it by, for option, this is, now I'm ready to do option 1, the first viewpoint, I guess, option 1, and we're going to multiply this by dx over dx. Okay? Remember, that's just, formally that's just the number 1, and I'm going to actually manipulate these differentials, which is, again, where some people might take objection, but their loss. So I'm going to go ahead and bring into the square root, I'm going to bring in one of those differential x's that I just multiplied this by. So I'm going to bring into the square root, let me put a little bracket there, I'm going to bring inside the square root the differential x in the denominator, and because I'm assuming that differential x is positive, and I can pass it inside the square root this way and bring it in as 1 over differential x squared, with leaving a dx sitting outside here. Okay. If I distribute that differential x to both terms in that square root, I would have differential x quantity squared over differential x quantity squared plus differential y quantity squared over differential x quantity squared, and then the remaining differential x sitting on the outside here. Okay, well, we can see that I could replace this expression formally with just 1, and here we have dy dx quantity squared. So I'm going to rewrite this as the square root of 1 plus dy dx quantity squared differential x. And so what was our original strategy? Our original strategy said, well, we're going to add up each of these DL segments. So each of these DL segments that we have here, if we sum them up, that's going to give us an approximation for the length of this curve. So we're going to sum them up from point P to point Q. And so if we integrate those DL segments, we're adding them up from P to Q of differential L. That would be the same thing as integrating on this side from x equals A to x equals B of the square root of 1 plus dy dx quantity squared differential x. And so here we get the first statement for the length of the curve, the integral from A to B of the square root of 1 plus dy dx quantity squared dx. Okay, so I said I'm going to do 4 viewpoints. That's sort of a lie. The next viewpoint is really just turning the tables and thinking of this function dy dx here. Rather than thinking of the curve as a function of x, we're going to think of it as a function of y, and that's again why I needed this to be 1-to-1. Okay, so option 2 is really just to repeat this process. So I'm not going to do all of the steps for this, but it's to go back to that statement that dl is equal to the square root of differential x quantity squared plus differential y quantity squared. And this time I'm going to repeat the whole process, but I'm going to multiply it by differential y over differential y. And then again, I'm going to pass this differential y here inside. And when we clean everything up, we'll end up with the expression that differential L is equal to the square root of dx dy quantity squared plus, and notice this would give us differential y squared over differential y squared, so that's just going to be the quantity, or the value 1 times differential y. So now integrating both sides, we get the length of the curve on the left side, and on the right side we'd have the integral from y equals c to y equals d of the square root of dx dy quantity squared plus 1 times differential y. Okay. So I'll just go ahead and add these y equals c, y equals d, as opposed to x equals a, x equals b, but that fits with our original picture here. So zooming way up, here we had x equals a was our left endpoint, x equals b was our right endpoint, versus y equals c, which was our lower endpoint, and y equals d, which was our upper endpoint when we choose to integrate with respect to y. Okay, so these are the 2 viewpoints of arc length that are usually presented in Calc 2. And then sometimes this is encountered in Calc 2, sometimes it's encountered in Calc 3. It doesn't really matter. The next way to visualize this or to think about this is to take that parameterization that I was talking about. So for option 3, I'm going to go ahead and say let the curve, I think we called it C, let C be parameterized by this function that we gave before. P of t maps from, it takes the real number t and it's going to map it somewhere into the xy plane, and it'll do so by taking t and mapping and giving it to, assigning 2 coordinates to it, where the first coordinate is some function of time and the second coordinate is some function of time, and that's for and usually I'm going to restrict this to alpha to beta, so time is some value in between these 2 endpoints. Okay. So I'm again going to return to that differential L statement. I mean, again, this all hinged on the Pythagorean Theorem. That's where we came up with this original statement here. So I'm going to return to that again in this viewpoint. And so differential L is the square root of, and now instead of writing differential x quantity squared, I'm going to write differential x of t quantity squared plus differential y of t quantity squared. And again, I'm being very loose with the notation here, but this is a quick way to get to arrive at the arc length formulas without having to use proper limit notation, etc. So the trick here then, similar to before, in each case we took this differential L description and we multiplied by something. Same thing we did here. We multiplied by dy over dy. So over here I'm going to multiply by differential t over differential t. And I'm going to do the same work, passing everything inside the square root here. So we'll show one step of that. So we've got parentheses differential x of t quantity squared plus differential y of t quantity squared. And that's all sitting inside the square root. And then we're going to pass inside the square root, we're going to pass in one of these differential t's, the one in the denominator. So we bring that in as 1 over, get that out of the way, that's not quite big enough. We bring that over as 1 over differential t quantity squared, differential t. So again, I guess here I'm making the assumption that differential t is greater than 0. And folks, if differential t wasn't greater than 0, I would have to then place a negative sign outside here, but everything would work out in the wash at the end. So it's just a quick, convenient assumption that we make. It doesn't actually change anything. Okay, so again, I'll take this differential t and distribute it here, and what we end up with is the square root of differential x dt quantity squared plus differential y dt quantity squared times differential t. And again, we'll integrate both sides, so I'll show this step one last time. The integral from p to q of differential L is equal to the integral from t equals alpha to t equals beta of the square root of, and let's go ahead and use the prime notation, x prime of t quantity squared plus y prime of t quantity squared differential t. Okay, so I've said I'm going to do 4 viewpoints. These first 3 viewpoints all sort of require the same manipulation. I think of these 3 viewpoints, this last one that tells us the arc length, and I should have said here that gives us the arc length is the integral from alpha to beta of the square root of x prime of t squared plus y prime of t squared differential t. So of these 3 viewpoints, I think this one's probably the most convenient. You parameterize the curve because that allows you to handle situations like this curve over here, where we think of it as the curve is being traced out by time. We think of this curve as being traced out by time as time passes along, and that's a more convenient way to think of this. And anyway, but all 3 of these are essentially giving us the exact same arc length formula. So the last viewpoint that I want to do, this is more of a Calc 3 viewpoint, a vector calculus viewpoint, and so this is what I'm calling option 4, and I think this is the most interesting of the viewpoints, and we'll see why. So in this case, we're going to let C be parameterized, not by some parameterization function, but by a vector valued function. So by the vector valued function, the vector valued function r of t, and we'll write it in column notation, so there's x of t, y of t for alpha less than or equal to t less than or equal to beta. So this is the same, these, you could use the same parameterization functions that you use in that p of t under my third viewpoint. That would be fine. But instead of thinking about this as you plug in a time value, so let's see here. Up here what we thought of is you plug in a time value and it spits out an ordered pair. Here we're going to think of we plug in a time value for t and it spits out this vector. Okay? So just in case you're a little rusty with these parameterization vector valued functions, one way to look at that is, let's go back to that original picture, and here we've got, I guess actually I don't have to draw the original picture. This doesn't require that it be 1-to-1 anymore. But one way to look at this is that, for t equals alpha, we would figure out what vector we get when we plug in alpha, and that would spit out, let me do that in a different color, that would spit out this vector right here. So there's the vector r of alpha. And when time equals t naught, here we'd have r of t naught. And when time equals beta, and this is I'm gonna erase this because this diagram's getting a little cluttered, but there would be r of beta. And so we see then under this way of thinking about it, we don't require that the curve be 1-to-1 in the x or y direction. Everything will work just fine. Okay, so let's look at this a little more closely since that diagram got a little cluttered. And here's this curve again. This endpoints when t is equal to alpha. This endpoints when t is equal to beta. And instead of thinking about chopping this up into little segments of length, what we're going to think of is at various points, at sample points throughout here, we're going to go ahead and compute the tangent vector here. So the tangent vector is some r prime of t naught. That gives us that tangent vector. And then we could take some other point right here, and we could find its tangent vector. And so this is, maybe some, I guess I probably got myself into trouble with the notation. We'll call it T1. So there's another tangent vector, and at various points here we have these different tangent vectors, and so rather than thinking about summing up a bunch of little segments, which was our original viewpoint for all of this, was summing up a bunch of little segments over the interval, instead what we were going to do is we're going to sum up the lengths of a bunch of vectors. So let's say that again. Okay? So we're going to say that the arc length can be thought of as the integral from t equals alpha to t equals beta of the sums of a bunch of tangent vectors. So the lengths of a bunch of tangent vectors. So I'm going to go ahead and first give the formula this way: r prime of t differential t. So this is the length of a tangent vector. So even though this function is has coordinate functions, so in a sense we're still using the Pythagorean theorem. When you compute the length of a vector, you've got the square root of you'd have this, if you wanted to compute the length at a point, you'd have x of t quantity squared. You'll be a little careful here. This is the derivative already. So y prime of t quantity squared. It's still, the Pythagorean theorem is still there, but we can sort of use vector notation to avoid having to write these square roots, and we just use the magnitude expression, that is taking the length of the vector rather than writing our square root out, which makes the whole formula a little bit more elegant. But this is the last thing I want to say, and this is why I think this fourth viewpoint is the most important viewpoint. We're going to take the integral from alpha to beta. What's another way of writing the derivative function of r? Well, we could think of the derivative, if this is a position function, which we're imagining it is, we can write the derivative of a position function, a position vector valued function, as a velocity function. And all of a sudden we have this new way of thinking about this. To find the distance between, or along this curve, what are we going to do? We're going to add up the lengths of tangent vectors. That viewpoint is very similar to our original viewpoint, but another way to say that is, if these are tangent vectors' lengths, we're adding up the speed, and this is the whole point of this video, I think. This is adding up various speeds over small intervals of time. Because each one of these little vectors here, its length is simply the speed of the object at that point in time, and then we allow that to we consider that interval over a small interval of time. And so what are we returning to? We're returning to a very fundamental idea in physics, that distance can be thought of as the speed that the object's traveling, rate, times some increment of time. So we're returning to that distance equals rate times time when we say that the arc length, let me go ahead and sum it up one more time here, when we say that the arc length is equal to summing up a bunch of rates times times. There's the rate, there's the velocity vector, and when we take its absolute value, this is the speed vector. So there's your rate, there's your speed, times a small increment of time. And so we're back to the original idea that distance is equal to rate times time, and it's this fourth viewpoint which I think is the most useful when computing arc length.